All right, now that we're done with the E2 reaction, let's cover the E1 reaction. So E1 stands for unimolecular elimination reactions or elimination unimolecular reactions, whichever one you want to think about. These are similar to the SN1 reactions, so they generally occur through the same reaction conditions. And so anytime you have an alkyl halide that is placed in conditions that would lead to SN1 reactions, it would also lead to E1 reactions. So they generally go hand in hand. So here's an example. We're using a terbutyl alkyl halide. If we put it in a protic solvent, the halogen would leave, form a carbocation, and then we would either get substitution to get this product, or we would get elimination by removing one of these hydrogens on the methyl groups, leading to a double bond, let's say there. So that would give you the E1 product. Uh, as shown here, and is true for most cases, usually SN1 would be favored over E1. So the conditions that lead to one would lead to the other, but usually SN1 products are favored over E1. The rate equation for an E1 reaction is first order overall, as shown by this equation. Rate is equal to K times the concentration of the alkyl halide. Very similar to an SN1 reaction. The rate equation, as shown here, notice it points out that the reaction is only dependent on the concentration of the alkyl halide. It doesn't matter how much base we use, it doesn't change the rate very much. So one other thing to note about E1 reactions is that they have no conformational requirement, unlike the E2. E2 reactions require the anti-periplanar geometry in the reactant. We don't need to worry about that for E1 reactions. The E1 reaction mechanism occurs in two steps. So the first step is for the halogen to be eliminated, forming a carbocation as shown here. And then in a second step, the base would remove this hydrogen on an adjacent carbon to form a double bond there. The first step is rate determining or rate limiting. We get to the carbocation, and then the next step is really fast. There are differences in how cyclohexanes with halogens on them behave in an E1 reaction versus an E2 reaction. So on the left, we have ideal E2 conditions. So we're using a large amount of base and we have an alkyl halide involving a cyclohexane ring. So if we add base, the base would remove a hydrogen that is axial on the adjacent carbon to the carbon that has the leaving group. So the base will remove this hydrogen, form a double bond there by eliminating the chlorine. So there's the product. Notice this hydrogen here is not touched because it's equatorial, as we discussed before. This compound here, or this structure here, is the same same compound as we started with. It is, however, reacting under E1 conditions. Under E1 conditions, it doesn't matter which conformation we have, whether it's the one on the left or the one on the right. So under E1 conditions, this halogen would be removed, forming a carbocation, and it would happen the same way here. Um, the the base would then remove a hydrogen on the adjacent carbons. So it could be this one or that one. We would get a double bond on the left, double bond on the right. And so we would have two possible alkene products when we do this under E1 conditions. Again, that highlights the fact that the anti-periplanar geometry is not required for the E1 reaction. If you look closely at the conditions here, you might wonder, how are these E1 conditions? Well, the base, although it's a relatively strong base, is used in a very small amount. So it's really hiding the fact that these are E1 conditions. We're using protic solvents, very little base, so it favors E1 conditions. Here, however, although we're using protic solvents, which is not ideal for the E2 reaction, we are using a ton of, or a very large amount, so 1 molar versus 0.01 molar, a large amount of base here. So this is a very strong base. It favors E2 conditions.